Right, welcome back to your Chem 4 lecture. This time we're moving on in chapter 11. We're going to talk about alkenes and alkynes in this lecture. And we have a very brief video on aromatic compounds in the next lecture that we're going to take a look at just very briefly. Now, you might ask yourself, we studied saturated hydrocarbons that we were calling alkanes, and those saturated hydrocarbons are all single bond, carbon-carbon single bond organic compounds. So what's the difference between alkenes and alkynes? As you may guess, we said the word carbon-carbon single bond quite a bit in the last video. So for alkenes, they contain a carbon-carbon double bond, at least one of them, and then alkynes contain at least one carbon-carbon triple bond. Now, these are referred to as unsaturated hydrocarbons to distinguish them from alkanes. And the reason that we say that is essentially they don't have the maximum number of hydrogen atoms. So like a hydrocarbon that is saturated with hydrogens has the maximum number of hydrogen atoms that's saturated. That's an alkane. These, because they contain carbon-carbon double or triple bonds, there's carbon bonds that are not to hydrogen. So that means that there's more hydrogen atoms we could fit on a molecule if we just broke those double and triple bonds. Now, all of these, we're going to talk about hydrogenation. When you combine these alkanes and alkynes with hydrogen in the presence of a particular catalyst, you can turn them into alkanes. Okay, so alkenes first. We're going to talk about alkenes because that's the simplest step up. They have to have one or more carbon-carbon double bonds. Ethene here is C2H4, and it's the simplest alkene that there is because it's just two carbon atoms that are connected by a double bond. Now, you may already kind of get an idea of how we're going to name these things, right? Remember, the two carbon alkane is ethane, the two carbon alkene is ethene. And so you can kind of guess already how we're going to do that. Now, when we actually draw the line angle structure for ethene, we're going to put a double bond, obviously, between carbon and carbon, and then any substituent groups. These are all hydrogens here, but because this carbon is bonded to 1, 2, 3 other atoms, that means it's trigonal planar in structure rather than tetrahedral, like what we saw with the alkanes. So the bond angles should all be drawn at about 120 degree bond angles. So ethene is more commonly known as ethylene gas, and it is actually a plant hormone. Plants send this out when they're ripening to promote the ripening of the neighboring plants, basically. That we associate as the breakdown of cellulose in plants, for example. So the way that you can actually keep fruit a little more stable for shipping purposes is if you keep it in a no oxygen, no ethene container, and you ship it, then once you get close to where you want to distribute the fruit, then you can dose it with ethene gas, and that tells the plants to ripen up. Okay, alkynes, on the other hand, of course, have triple bonds. So, for example, ethyne is the simplest one. That's, again, you need two carbons to have a double or a triple bond. So ethyne is the alkyne, C2H2, that has a triple bond between its two carbons. And then each of those carbons then has one hydrogen on it. Again, we can always use our principle here that each carbon has 4 bonds, because remember, this carbon has a double bond, so that's 2, and then it's bonded to 1, 2 other hydrogens, so that's a total of 4. So you can think of it that way as a way of making sure you keep track of all the bonds. And then down here for ethyne, this carbon-carbon triple bond, so this carbon has 3 bonds to 1 carbon, plus a bond to a hydrogen, that's 4 total. Note here for the alkyne, because it's got this triple bond here, this carbon is bonded to 1 carbon, 1 hydrogen, so 2 total bonded atoms. That means that it's going to be linear, or the bond angles are going to be 180 degrees. So that does significantly change the way that you draw alkynes when we get to that. Okay, so we're going to start it easy. Just take a look at A and B here. Identify it as either an alkene or an alkyne based on what we've talked about. So go ahead, pause the video. Let me take a sip of my tea. And when we come back, we are going to go ahead and just give you the answer here. Okay, so clearly what you're looking for here is we have line angle drawings of two different organic compounds. What you're looking for is double or triple bonds. Well, this right here is double bond. Remember, we were drawing alkanes like this. So to draw a double bond, all you do is you take whatever bond you're talking about and put a second line there. And that's telling us that there's a double bond from this carbon to this carbon. So this is an alkene. Down here, this is an example of an alkyne. Now all of a sudden, well, let's kind of do the model up here and I'll show you what's wrong. So with this down here, we've got 1, 2, 3 bonds from this carbon here to this carbon here. So clearly that's an alkyne. Now, the way that you draw it is, imagine that you draw the alkane. We did a double bond here, and then below it, we're going to put a triple bond. But there's a big problem. This carbon and this carbon are both supposed to be linear. Do they look linear from the way that we drew them? I don't think so. So you actually need to straighten it out to show that these carbons are linear when you draw your line angle drawing. So you do carbon 1 to carbon 2, and then we've got a triple bond from carbon 2 to carbon 3, then carbon 3 to carbon 4, and then carbon 4 to carbon 5. So both carbons 2 and 4 are linear in their geometry. And then this is the correct answer for an alkyne, and this would be incorrect. That's not the correct drawing. Okay. Oh, and let me clear my drawings. And yeah, sure enough, alkene and alkyne. Okay. So now some good news. We learned the alkane system nomenclature, and that's mostly going to apply for alkenes and alkynes, especially for very simple ones. For example, the first two, ethane, there's only one carbon-carbon bond. So you just draw a double bond there, that becomes ethene, triple bond, that becomes ethane. And also it works out for propane as well, because here we have 1, 2, 3 carbons. And if we draw a double bond between carbons 2 and 3, that becomes propene, and then a triple bond would become propyne. Now you might ask yourself, well, what if we didn't do that? What if we drew the double bond between carbons 1 and carbon 2? Well, this molecule that I just drew here is the same as this one, because you can take it and flip it. And if it flips and it overlaps, that means it's the same molecule. So therefore, we don't need to say, what atoms propene has a double bond between, and same thing with the propyne. Okay, all right. Now it gets a little more complicated from there. So we're going to go ahead and do these here as examples together. Oops, where did I go? There we go. Now, if you're feeling ready just to give it a shot, go ahead, pause the video and give it a try. But I do think this is a little more complicated than we're letting on here. So I would like to show you how to do this. So if you're feeling confident, go ahead, pause the video, and we'll come back in just a second. If not, stick with me and let's go ahead and name these out. So step number 1, we want to identify the longest hydrocarbon chain. But this time, we specifically have to include the multiple bond. So we have to specifically include either the double bond for A or the triple bond for B. So I'm going to start here. It's carbon 1, 2, 3, 4, and then we'll go this way, 5. You could go this way for 5 as well, but I think we see that that's equivalent. So there's no real need to do that. Okay, so that means that our longest chain is pentene. Or I'm sorry, we have our longest chain is 5 carbons. So that means it would be pentene as a alkene. That's how we name it, right? Rather than pentane, it becomes pentene. Now, the problem with pentene is that actually it does matter where we place the double bond, because you could have pentene like this, what we have here, or you could have pentene like this. Clearly, this is not the same as this, because here the double bonds between carbons 1 and 2, here are the double bonds between carbon 2 and 3. So what we're going to do is we're going to write a number in front of the word pentene here that tells us the first carbon atom that's involved in the double bond. Since the first carbon atom involved in this double bond is 2, this becomes 2 pentene. Over here, this would be 1 pentene. Sorry. There we go. Okay. Now, you might ask yourself, but Professor Dowd, we have a substituent at carbon 4. Don't we want to number the thing the other way? Well, the truth is now the double bond takes priority over the substituent. So the double bond is going to be numbered first. It's going to be the lowest number, and then the substituent is numbered after that. So always start your chain from the closest side to the double bond. And then to round it up, we have a methyl group on 4. So the final answer here should be 4-methyl 2-pentene. Now, there is another way to write this that you may see. I'm not sure if your homework is this way, but just to give you an idea, you can also see it as 4-methyl, and then it would be pent 2-ene. So I definitely make like my organic chemistry students in 12A write it this way. This is a better way to write it, but this is kind of a simpler way to write it. The reason that you might write it this way is because in the future, there's other things that we put on the end here. So having a 2-pentene, if you have an alcohol as well, that goes on the end, and so it gets confusing. But I think for the purpose of this class, it's totally fine to just do 2-pentene. Okay, now give B a try here. If you feel confident from what I just said, go ahead, give it a shot. If not, we'll walk it through right now, but we have the opportunity to pause the video here anyway. Okay, so down here, we're going to start from the side closer to the double bond, so triple bond in this case. So that's carbon 1, this is carbon 2, this is carbon 3, carbon 4, carbon 5, carbon 6. So I got a 6-carbon chain. Now this can be really difficult to see sometimes because we're used to counting like the bends, right, in our structures. But with a alkyne, there's no longer a bend. There's a carbon here, carbon 2, and that is a straight shot to carbon 3. So you just have to look, okay, this is where this triple bond ends. This is where this triple bond begins over here. And so that's got to be 2 carbons there in between carbons 1 and carbon 4. Okay, so we've got hexyne because we got 6 carbons and it's an alkyne, so hexyne. And then we've got the triple bond between carbon 2 and 3. So what should we number it? Well, we go with the lower number, right? So 2-hexyne. And that does it. That's all we need to do there. Oh, okay, so let's just make sure. Yeah, 2-pentene, 4-methyl 2-pentene, and 2-hexyne. Okay, great. All right. And just to kind of like go back through this thing here, because they do it here. So you always want to start numbering the chain from the end nearer the double or the triple bond, and then finally, add the substituents like what we did before. Okay, now there's another separate rule for cycloalkenes. Cycloalkenes, as it says, they're cyclic, just like cycloalkanes were. Cycloalkenes have a double bond somewhere in the ring. And the way that you name it is, of course, you just use the alkene name with the number of members of the ring. So like cyclopentane becomes cyclopentene. But the first 2 carbons are always going to be the participants in the double bond. So the double bond is going to tell you how to number it. So in this case, we have a double bond between these 2 carbons. So we know that they've got to be 1 and 2 in some order. And then we have a methyl group next to carbon, this side of the carbon. So when we number it, we're going to want to number it 1, 2, 3, like what we see here. Now, technically, you could do 1, 2, 3, 4, 5, but that would increase the numbering on this substituent here. And remember, we always want to reduce the number when we can. So 1, 2, 3, that gives us a methyl group on the 3rd carbon of the cyclopentene. So this is a cyclopentene ring because we have 5 carbons in a ring, and they've got a double bond. So again, cyclopentene. Then the numbering has to go, these 2 have to be 1 and 2. So 1, 2, 3, there's a methyl group on the 3rd carbon. So it becomes 3-methyl cyclopentene. Okay, so why don't you go ahead and give these 2 a try based on what we've learned already. Now this I think you should be able to do based on what we learned in the last lecture. So please pause the video now, give this sample exercise a try, and when you come back, we'll take a look at the answer. So go ahead, pause. Okay, let's go ahead and take a look at our answers here. So on the left side here, we've got a ring that has 1, 2, 3, 4, 5, 6 carbons. So it's the cyclohexane hexane, but we've got a double bond, right? So we know that it's going to be cyclohexene. And then there's no substituents, so we don't have to worry about that. It's just cyclohexene. Okay, same thing over here. Now count the carbons in your ring. 1, 2, 3, 4, 5. So once again, we have cyclopentene. But now we do have substituents, right? Now we know that these have to be carbon 1 and carbon 2 in some order. So we want to number it so that we reduce the number of the substituents that we have over here, right, for this carbon. So it's got to be 1, 2, then 3. Because if we went around the other way, this would be 5. So of course we want 3. Now on 3, we have a methyl group and a methyl group. So that's dimethyl, right? So when we write out our substituents, it should be 3, 3 dash dimethyl cyclopentene. Close enough. There we go. So that's all you have to do. All right. Oh, actually, let me clear those drawings and we'll go through the answers here. Yeah. All right. Now, there's another type of thing that we have to worry about with alkenes in particular, and to a lesser extent, alkynes. I don't think we even talk about that in this class. So let's not worry about that. Let's worry about alkenes in particular, which is a different type of isomerism. Now, in the previous lecture, we talked about isomers, in particular structural isomers. Those are molecules that have the same molecular formula, but have different bonding arrangements. Now, with double bonds, it's even more complicated because you can have the same bonding arrangements, but with different arrangements in space. So in other words, you have the same types of bonds, but the double bond, as we're about to find out, is fixed, okay? So let's go ahead and take a look at 1,2-dichloroethene. So 1,2-dichloroethene, it looks like this, basically. You have a carbon here and a carbon here, and then you have a chlorine on both of them, and a hydrogen on both. Now, here's the thing, and we don't talk about this much because, we just have a lot to cover in this class. We run out of time here, but this double bond here, it does not rotate. And you'll see this with the models that we have in class. The double bonds don't rotate. They just cannot rotate. So, whereas single bonds do rotate around an axis. So with the double bond, with these two chlorines being both pointing up here, they're stuck in that position. Now, you can imagine another form of this molecule, 1,2-dichloroethene, where one Cl is up and the other Cl is down, like what I'm drawing here. Now, because this double bond doesn't rotate, that means that these two molecules are different. They're different in space. You can't, directly overlap them. So that means that they are different molecules. And this is what we call cis-trans isomerism. Cis means same. So when you have a cis isomer, that means both of the groups, in this case, the chlorine groups, are on the same side. When you have a trans isomer, that's when the two groups are on opposite sides, in this case, the chlorine atoms. And the way you kind of represent it is with your hands. Imagine that your fingers are the double bond here, okay? And in this case, if our groups are both pointing up, that's clearly going to be a cis isomer because they're pointing to the same side. If they're across from one another, like this, that's an indication that you have a trans isomer. Okay. Similarly, butene has this same problem. So you have 1-butene or 2-butene. We're talking in particular about 2-butene. This is where we have methyl groups on either side of an alkene. It can either be cis 2-butene or trans 2-butene, whether those methyl groups are on the same side, that's the cis isomer, and then whether they're on opposite sides, that's the trans isomer. Okay. So that's just a kind of brief look at isomerism there. One thing that we want to look at with particular interest with alkenes is pheromones in insects. So pheromones are chemicals that other species can detect that maybe we can't. You think of it like smelling, right? Even if it's a different type of a sense, but insects, for example, commonly use pheromones to warn of danger, to mark a trail, like what ants do, and then also for attraction, if they want to attract opposite sex of them. The ability of these to transmit will depend on the cis or trans configuration of the double bonds. The most famous pheromone is bombicol, and this is the female silkworm pheromone, and it has a cis double bond and a trans double bond. So just so you know, like if those were swapped, or if they were both cis or they were both trans, then the pheromone wouldn't work. It doesn't hit the same receptors for notifying, in this case, the male silkworm moth. Okay, so now how do we name cis trans isomers? Well, the main thing is to be able to identify it, right? In this case, we have a bromo group on carbons 1 and 2 of ethene. If they're on the same side of the double bond, like what we do here, this is the cis 1,2 dibromoethene. On the other hand, if they're on the opposite sides, it would be trans 1,2 dibromoethene. And yeah, so we just use the words cis or trans as a prefix in front of the name of the alkene when we worry about cis or trans isomers. Note, not every compound has a cis or trans isomer. If you have a compound that has the same substituents on either side, so for example, take a look at this. What if we had, let me draw the compound first and then I'll name it for you here. If we had 2-methyl propene, it would look like this. In this case, we've got both hydrogens on one side, so there's no primary group over here. Likewise, this carbon over here is symmetrical. It's just got 2 methyl groups. If you flipped it, nothing would change, right? It'd be the exact same molecule. So that is not cis or trans. Only in this case where we have like asymmetric groups on both sides. So carbon 1 has a bromine and a hydrogen. Carbon 2 has a bromine and a hydrogen. Only in this case can we have cis or trans isomers. Okay, so let's give it a shot here. Why don't we name each of these using cis or trans when needed? So let's go ahead and start with, I'll do A with you here, and then we will, I'll let you do B and C on your own. Of course, you can pause the video at any time if you feel like you're ready to tackle this. Okay, so first up, let's go ahead and count up the number of carbons that we have here. I've got 1, 2, 3, 4, and it's an alkene. So it seems like it's 2-butene to me. So 2-butene is a good place to start. Now our substituents here, we've got a chloro and a chloro on groups 2 or carbons 2 and 3. So 2,3 dichloro. Butene. All right, and then are those cis or trans isomers? Well, it seems like they're on the same side of the double bond to me, right? You draw a line between them and it doesn't cross the double bond. So that seems like it's a cis isomer to me. So I'd call that cis 2,3 dichloro 2-butene. Okay, so why don't you go ahead and give B and C a try, and then see if you can come up with the correct answers here. So pause the video here, and when you come back, we'll take a look at the answers. So pause. Okay, all right, are you back? Well, let's go ahead and first just identify whether it's cis or trans, right? So here, this carbon has a methyl group and a bromine, so that's 2 different things. That means it could be. And this carbon here has a bromine and a methyl group, so that's 2 different things. So this one definitely could be cis or trans. And as we see here, our bromines are on opposite sides of the double bond. If you draw a line between them, it crosses over. So that's trans. And this one up here, remember this one was cis. And down here, this carbon has a methyl group and a hydrogen. This carbon has a methyl group and a hydrogen. So definitely cis-trans isomerism is possible. And then we have our 2 methyl groups here. They are across the double bond from one another. So that's, again, a trans isomer. Okay, then to finish up the names, well, here, we can just do that live together. I'll just walk you through. So we know in this case, again, we have butene, right? 2-butene. All right, and then we have bromo at carbons 2 and 3. So 2, 3 dibromo, 2-butene. And then we agreed it was a trans isomer, right? So B should be trans 2,3 dibromo 2-butene. Down here, just looks like 2-butene to me. No halogens or anything bonded there. And then the methyl group's on opposite side, so I'd call it trans 2-butene. Okay, so let's take a look at the answers here. Yeah, sure enough. Okay, so finally, what we're going to talk about is addition reactions that take alkenes and turn them into alkanes. So you take unsaturated hydrocarbons and turn them into saturated hydrocarbons. So the reaction that always goes over is basically you add hydrogen gas, H2, or you add water, H2O, to the carbons in a double or triple bond. And what you produce is either an alkane in the case of having H2, or an alcohol in the case of adding water. So these alkenes and alkynes provide really reactive bonds that we can use to do reactions that we can't otherwise do. So it's easy to break them, and so it's easy then to form new bonds. Hydrogenation looks like this. Hydrogenation is exactly what it sounds like. It's the addition of hydrogen. And what it does is it takes a double bond or a triple bond too, and it adds in the case of an alkene, one equivalent of hydrogen, and that both of these then form new carbon-hydrogen bonds, breaking the double bond and forming these two new carbon-hydrogen bonds. Note that you have to use a catalyst like platinum, nickel, or palladium in order to actually do the reaction. And then I guess we're not going to really talk about it too much, but hydration is very similar. You take an alkene and water and you produce an alcohol. So just instead of having two new CH bonds, you have one COH bond. And we'll talk about that more when we get to the alcohol chapter, which I think might be the next one. Okay, so this is pretty lame, but I guess we're just, show me what happens when you hydrogenate 1-butene. And I particularly want the equation for the reaction. So go ahead, give it a shot. Try to write out the equation similar to what we saw here, but this time we're talking in particular about 1-butene. So tell me what the product is going to be out of that. So go ahead, pause the video now, and when you come back, we'll take a look at the answer. Okay, so the way you want to draw it is, and I would draw this personally, I always use line angle drawings because I find they're simple. So you take 1-butene, which would look like this, right? 1, 2, 3, 4 carbons, double bond between carbons 1 and 2. You're going to add in hydrogen gas, H2, and you use a platinum catalyst. And what do you get? Well, you break the double bond and you form two new carbon-hydrogen bonds. So you get just, whoops, you just get butene out of it. You don't form any new carbon-carbon bonds. So you get from 1-butene to butane, just like that. Okay, now where this actually shows up a lot is in the industrial process of making margarine. So, so there's a difference between animal fats and vegetable fats that you might be familiar with. So like animal fats would include things like lard or beef tallow or butter. Those tend to be very high in what we call saturated fats. And it's exactly what we've been talking about, where saturated compounds have more single bonds. Unsaturated compounds have double or triple bonds. But the problem is those animal oils tend to be more expensive than the vegetable oils that you can get from things like olive oil, for example, canola oil. There's many different types of vegetable oil. So a long time ago, chemists came up with a way to take those vegetable oils and turn them into something more like the animal oils. And that's this hydrogenation process. So for example, oleic acid has a double bond in it. And this is something that you can get from olive oil and other vegetable oils here. If you undergo hydrogenation, you get a single bond and you form this stearic acid here. This is actually found in saturated fats, like butter, for example. And so you take something that's an oil, a liquid at room temperature, and turn it into something that's more of a solid at room temperature. For example, margarine. So there's a difference between margarine and butter. Margarine is a vegetable oil that's been chemically processed into a saturated fat, whereas butter is it's saturated from the beginning. Okay, so go ahead, give me the product of each of these, keeping in mind basically just hydrogenation. You get rid of the double bond and you turn it into two new carbon-hydrogen bonds. So go ahead, pause the video here, come up with what the products of these are going to be, these hydrogenation reactions, and then we'll look at the answers when you come back. So pause. Okay, so we're back. Let's go ahead and take a look. So in this case, it's 2-butene. That just becomes butane. And cyclopentene here just becomes cyclopentane. Again, we get rid of the double bond and we just form all new carbon-hydrogen bonds. Okay, so we are going to talk about hydration. Sorry, I forgot that we have this here. So with a hydration reaction, this is where you take your alkene and you react it with water, and basically you break the double bond, the carbon-carbon double bond. And the two new bonds that you're going to form are a carbon-hydrogen bond and a carbon bond to an OH group. And now this right here, this is what's called an alcohol. Okay, so this OH group is what determines something that's an alcohol. Now, what's important about alcohols is that having this OH group allows it to hydrogen bond with water. And so it tends to be that alcohols are more soluble in water than other organic compounds. For the catalyst for this reaction, you just need to use a strong acid, but usually it has to be something like sulfuric acid, like a very, very strong acid, for it to actually go. Let's see, was there anything else? Yeah, okay. All right, so let's go ahead and now, what am I trying to tell you here? Yeah, okay. Okay, here's the important part that I almost forgot to mention to you. The OH is going to form a bond with the carbon that's already bonded to the fewest hydrogen atoms. So that's going to show up here in this next one. So let's see. Let's go ahead and clear this here. Okay, so based on what we know so far, we know that we're going to form CH3, CH2, and we're going to form something new with this carbon here, and something new with this carbon here. So we broke the double bond that was between these last two with this process. And now we're going to distribute an H and an OH to those carbon atoms. The OH group is going to go to the carbon that's bonded to the fewest hydrogens. So this here is bonded to 1 hydrogen. This carbon is bonded to 2. That means that this carbon gets the OH group, and this carbon just gets a hydrogen, like that. Yeah, so that's what you need to know about hydrogenation and hydration as far as the reactions of alkenes go. Now we're going to have a lot more of these in near chapters, but we're not going to spend a lot of time on the reactions of organic compounds because it's not going to come up too much for you in your professional capacity. So I want to make sure that we're focused on that as we move into biochemistry. Okay, so that does it for this lecture. Again, we have one more lecture this chapter, very short one on aromatic compounds. So just check that out now. I recommend because it's very short, and you'll just get everything done and be ready for the homework for chapter 11. All right, that does it for now. I will see you soon. Bye-bye.